So let me just give you another example. So I'm still going to be looking at this function, but let's change our constraint a little bit, just to give you a little bit more generalization. So here is the one method of finite, one subclass of finite elements called the discontinuous Galerkin. And if you do discontinuous Galerkin with the same function, okay, you're going to get something like that. So what's the difference between this approximating function from the previous approximating function? Well, one obvious difference is that, what do you see here?
It is not continuous.
It's discontinuous, exactly. It's discontinuous, okay? And but it's still piecewise linear. As you can see, within each element, we still get a linear approximation. So by loosening a constraint, we actually get a better approximation, right? We get a better approximation. But you're going to see that if we loosen some constraints, the resulting equations are going to be different. It's a little bit harder to solve. Why is it harder to solve? Because we get more degrees of freedom, right? So if you let's just count how many degrees of freedom do I have here in this approximating function, right? How many things I can change with this function? Anybody want to count? We have 10 elements, 10 intervals. Each interval we can have a different linear function, right? So how many degrees of freedom do we have? How many degrees of freedom do we have in tuning this piecewise linear but not necessarily continuous function?
11.
Huh?
11.
11? Why 11?
There's, well, it looks like there's 10 intervals, and then that's going to correlate to, Megan just said 20, but my initial guess was 11 still, because there's sort of 11 points that the piecewise linear sections are based on.
Okay, so I think here Megan also gave an answer, and Josh, you two actually give two correct answers for two different finite element methods. So
Right.
20 is actually correct for this case, right? Because we have 10 elements, and every element can be a different ax plus b, right? That's a linear function, ax plus b, right? A linear function has 2 degrees of freedom. You can think of it as a x plus b, so you can change a and b independently, or you can think of I can choose the left value and right value of the function on every interval, right? So for every element, I have 2 degrees of freedom. I have 10 elements, so I have 20 degrees of freedom. Okay, so that's for the discontinuous case. And for the continuous case, it's different. So here's a continuous function. If I have continuous function, then on top of these 20 degrees of freedoms, I actually introduces constraints to eliminate some of these degrees of freedoms. That's one way to look at it. How many constraints do I have?
9.
Yes, I have 9 constraints, because on the intersection of one linear function with the next linear function, I constrain these two functions to be continuous, and I have 9 such junctions, right? So I have 9 constraints. 20 minus 20 degrees of freedom minus the 9 constraints, I get 11 degrees of freedom left. That's one way of looking at it. The other way to look at it is that I can set the value of the function at these grid points, right? At 0, at point 1, point 2, etc., up to 1. And I have 11 such points, including the 2 endpoints. So that's 11 degrees of freedoms. Okay, so basically I have, in this case, in the continuous case, I have 11 degrees of freedoms. And in the in the discontinuous case, I have 20 degrees of freedoms. I mean, these are the degrees of freedoms, finite degrees of freedoms I can use, right, to solve really an optimization problem that minimizes the difference between the function I draw and the approximating function.